Welcome back to Guided Hacking. Today we dive into Linux exploit development to become more familiar with GDB and debugging on Linux, and in general exploit development on the Linux operating system. To get started, we first tackle some challenges from Phoenix, from exploit education, and in this part we will discuss Stack 5, demonstrating a basic buffer overflow. Luckily, exploit education provides us with a C source code of the challenges, so we don't have to reverse engineer the whole application using GDB or IDA. Taking a look at the source code for challenge 5 shows that we have a main function which prints some text and then issues a call to the function startLevel. StartLevel then declares a char array with the size of 128 characters. Afterwards, the gets function is called to store the input from stdin in the local buffer variable. Taking a look at the man page of gets shows that it has a warning section. Never use gets because it is impossible to tell without knowing the data in advance how many characters gets will read, and because gets will continue to store characters past the end of the buffer, it is extremely dangerous to use. It has been used to break computer security, and therefore fgets should be used instead. This means if we simply provide more than 127 characters plus the null byte as the string terminator as our user input, we will overwrite memory outside the boundaries of the buffer variable. So to get started, we navigate to the path of the Phoenix binaries, which would be opt Phoenix AMD65, and there we got all the challenge binaries. To load the binary into our debugger, we use GDB stack 5, which in my case will load with enhanced features. To learn more about how to set up the environment and Jeff, just check out my last article on Guided Hacking where I explain how to set everything up. From here on, we can use the disassemble command to first of all disassemble the main function. This shows that we have a call to the startLevel function right here, and afterwards we simply move 0 into EAX, which would be the return value of the application itself, and then use leave and return to return from the main function. To get a better understanding, we can use the disassemble command again, and this time disassemble the function startLevel, which shows that we have a call to the gets function at offset 15. Then we just have an op, a leave, and a return instruction to return to the caller function, in this case the main function. Before the call to gets, we set up the function argument, which would be the destination where the data should get written to, and due to the x64 calling convention, this parameter will be passed by the RDI register. We can see that in the instruction prior to the call, the value of the RAX register gets moved into RDI, and RAX has the address loaded at the address of RBP minus hex 80. To retrieve the information required and to get started, we set a breakpoint at the call to gets and then start the application. Thanks to Jeff, a hook stop automatically gets executed when hitting the breakpoint, showing the CPU registers, the current stack, and the assembly of the last few instructions, the current instruction, and the next few instructions. To obtain the destination address where the data gets written to, we can now simply say print and then, for example, RDI or RAX, since both contain the same value. As we can see, the data will get written to hex 7, FFF, and so on, DF60. Now we can use MSF pattern create to create a unique pattern string, as usual, and for example, use a length of 256. After doing so, we can continue the execution of the application in Jeff. This will lead to the program awaiting our user input, where we can now paste in the string we just created. As we can see here, we kinda successfully triggered a segmentation fault and the application crashed. Taking a look at the registers, we see that we successfully overrode the RBP register. As usually, we can take this value right here and use MSF pattern offset to obtain the exact offset, which would be 128. Now, since we gathered a bunch of useful information, we can get started with our exploit script. First of all, we have the offset, which would be 128, and then we can use some simple shellcode to spawn a shell. In this case, I'm using the following, which simply executes a syscall to execv with the parameter of binsh, so essentially calling binsh and by that spawning a shell. What we want to do in order to move the execution to our shellcode is putting the shellcode within our user buffer, meaning we prepend the shellcode with an opslet and then we put in our shellcode, And finally, we append a buffer to fill the remaining space before the override of the base pointer and the stack pointer. We can say that we want to create an obslet, so hex 90 of, for example, 32 bytes. Then we have our shellcode next, and then we want to create a second buffer, for example, also consisting out of nobs, times the length minus the length of the shellcode and minus the length of the first nobslet.